Hello, everybody. Here in this video, we would like to talk about degree of freedom, right? We know the macroscopic properties of the gas like pressure, volume, and temperature. A lot depends on a parameter called internal energy of a gas. We know we have already told you earlier that internal energy that is there inside whose absolute value cannot be measured. Absolute cannot be measured. Only change can be measured as final internal energy minus initial internal energy, right? It will be always changing whenever there is a temperature that is more than absolute zero temperature. Now, I would like to explain who is contributing, why this internal energy is happening, how can we explain that? To explain that, internal energy is because of what? It's due to motion of gas molecules. To motion of gas molecules. These gas molecules could be having three different kinds of motions. It could be translatory motion, it could be rotatory motion, it could be vibratory motion. But vibratory motion is significant only when the temperature is high, say more than 1000 Kelvin, otherwise we can ignore that. All these motion of the gas molecules contributes to the internal energy. To explain that, so we have a theory called something like a law of equipartition energy theory. What is that theory says is each degree of freedom. So before going to that, let me explain what do you mean by that degree of freedom itself. So degree of freedom, as the name itself says, that in how many ways a gas molecule has the freedom to move. If it has a freedom to move, correspondingly it will possess energies like translatory energy, rotational kinetic energy, and vibrational kinetic energy, right? So how many degrees of the freedom that it has? So depends on how many kinds of the motion that the gas molecule has. Translatory motion alone, rotatory motion alone, vibratory motion alone are the combined effect of all of them, right? So once I'll come back to the degrees of freedom in a while. But now I would like to say, according to law of equipartition energy, each degree of freedom contributes some energy to the gas molecule, contributes some internal energy that is equal to half of kT, where K is Boltzmann constant per mole, or half of RT, where R is universal gas constant, where R is universal gas constant, and this is per gram. So depending on how many degrees of the freedom that the gas molecule has, each degree of the freedom contributes an internal energy of half kT or half RT, depending on are you trying to study it in terms of moles or in terms of grams, right? So now once as you know the basics of that, we can consider different kinds of gas molecules and see what is the kind of internal energies that they have and correspondingly what we can study. We'll start our discussion by start talking about a kind of a gas called something like a monoatomic gas. So what is a monoatomic gas? A gas who is having only one atom or one molecule like a hydrogen. No, helium. Hydrogen is H2. Helium, it always comes only in one molecule format. Whereas hydrogen comes like H2, that's called like diatomic. Like nitrogen, it comes like N2. So we are not talking about a gas who is monoatomic, who is having only one molecule. When you talk about that one molecule, what kind of degrees of the how much of the degrees of the freedom it has. We would like to discuss that first. A monoatomic gas molecule can move translatory motion, can have translatory motion. It can move along x-axis. It can move along y-axis. It can move along z-axis. It has a probably a three-dimensional motion. Each of that is a degree of freedom for that. Here is 1 degree of freedom, here is 1 degree of freedom, here is 1 degree of freedom. So the total degree of the freedom that it has is 3 due to the translatory motion. Now if you want to talk for a monoatomic gas, what is a rotational kinetic energy? Does that has a rotational motion or not? Let's discuss rotational motion. It's a single molecule. If it has to rotate, it has to rotate around itself. These molecules are very small in size. So when they are rotating about their axis, the radius of gyration, that is the distance between the center of the molecule and the axis, is almost nil. That means its moment of inertia is almost nil, is very small. That means its rotational kinetic energy, if you remember the formula, half I omega square, is also very small. So when we are talking about monoatomic gas molecule, we ignore rotational motion because it's not having an axis. There is no big distance between the axis and the body itself. Body is moving about its own axis itself. And of course, we ignore vibrational kinetic energy as we are dealing with temperatures that are low. It's not high temperature. So in a nutshell, a monatomic gas molecule has only 3 degrees of freedom. As we said, each degree of the freedom possesses an energy of half RT. So if you combined all that, and if you come to this point, here we can say total internal energy of a monoatomic molecule is each degree of freedom half RT. Like that, there are 3 degrees of the freedom as we have explained. So it's equal to 3 by 2 times of R. We know the definition of a specific heat of a gas at constant volume is amount of heat required to raise the temperature of unit mole of gas by 1 degree centigrade. We know dq, first law of thermodynamics, du plus dw. But specific heat of a gas at constant volume means dw equal to actually pdv. But you are keeping the volume constant, so dv equal to 0. So dq equal to du itself. We have done all this in the earlier case also in thermodynamics. I'm just telling here also for the sake of completion. For 1 mole or 1 gram, n equal to 1, du equal to cv dt. So if you substitute that value here, cv dt becomes 3 by 2 r as you are writing in terms of change in temperature. This t can be also written like dt. So cv can be written like 3 by 2 times of r. And we know cp minus cv equal to r, cp equal to cv plus r. We found cv as 3 by 2 times of r and plus r. So it becomes 5 by 2 times of r. So we got the values of cp and cv of a monoatomic gas. That implies I can get the value of gamma. We know that gamma equal to cp by cv. We found cp as 5 by 2 times of r, cv as 3 by 2 times of r, that equal to 5 by 3. So for a monatomic gas, gamma equal to 5 by 3, that is 1.66. So we can find the value of gamma, we can find out what is du, and we can discuss all these aspects basing on this important concept called degree of freedom. One, say for example, if you want to write du by dq, du equal to n, CV dt. dq is n Cp dt. So this is Cp by Cv, that is equal to 1 by gamma. So for a monoatomic gas, 1 by gamma means that is 3 by 5. That is 0.6. That is equal to 60%. So what's the meaning of that? Out of the total heat energy dq supplied, in the case of a monatomic gas, 60% is used as du. If you remember first law of thermodynamics, dq equal to du plus dw. So this dq is 100%. You got du as a 60%. That means automatically dw equal to 40% itself. That means if you write anything like dw by dq, it becomes automatically 0.4 or 40%. So the very important point that you have to understand here is, in the case of a monoatomic gas, out of the 100% heat energy supplied, 60% is utilized to increase internal energy and to manage itself, and remaining 40% is used to contribute the external work done. So that's all about monoatomic gas. They became little lengthy. We'll deal about diatomic and triatomic gases separately. Thank you for watching.